Part 5 of the Introduction to Amateur Astronomy lecture series is entitled The Art of Astrophotography. So, in short, astrophotography is a hobby within a hobby. It's where the art of photography meets the hobby of astronomy. So, this can be a completely separate hobby for some people. There are lots of people that consider themselves amateur astrophotographers or even professional astrophotographers. And they're not really what you would call amateur astronomers, where they do, observing and stuff like that. They are purely about the photography aspect of this kind of very broad hobby that we have here. So here is the old venerable 35 millimeter SLR or single lens reflex camera. This is what I started with back in the mid 1990s when I got interested in astrophotography. My kind of first subject for astrophotography was first the Perseid meteor shower. I tried to photograph some Perseids in probably around 1995. But then I remember trying to get my first images of Comet Hyakutake back in early 1996. And back then I had a good old fashioned 35 millimeter camera. And back then you had to get a good camera. I used to have a whole list of these when I first started doing the series some 20, 30 years ago, well, maybe like 20 years ago. And maybe even some of the current batches of film that were really good for astrophotography. And doing this kind of astrophotography was really hard because sometimes you would have technical issues with the camera. You would never load the film quite right. It would become unspooled or get torn, and you would think you would take a whole roll of images, but you got nothing. So I'm kind of glad this form of astrophotography is extinct. There we go. It's long gone, and thank goodness. Now, as always, there are some great books out there. There is, again, tons of information online, but there's a lot of great information in books. It's just kind of the bad thing about books and astrophotography is this area is changing so much. You can give general bits of advice, but you can't really give advice on equipment and maybe even image processing because it changes all the time. But there are some great books out there. I had to mention this one, of course, The Art of Astrophotography, because that's, of course, the title of today's lecture. But I came up with this title. I'm sure I'm not the first to do it. Again, roughly 20 years ago when I first started doing this series. So, Ian, I'm sorry I beat you to it, but he probably has the copyright on it. But that's okay. So here's just a couple of others. I'll just kind of mention this in quick passing, but perhaps the best types of books on astrophotography are digital because they can be quickly updated. So one of the friends of the club, Jerry Rodriguez, he has the series of kind of web-based books where again they can be easily updated. I know Jerry's largely retired now. I'm not sure how active he is anymore, but many of these should still be available for purchase and should be reasonably up to date. So you can check that out if you like. The one digital book that I do own here is the one from our friend Alan Dyer. He's a good friend of the Kalamazoo Astronomical Society, given several lectures and even attended several of our events. So if you're just going to do more of the nightscape type stuff with a simple camera and lenses and tripods and maybe some star trackers, as we'll talk about today, then I highly recommend How to Photograph and Process Nightscapes and Time Lapses. It's mainly available for those with an iPad, but there is a PDF version too. The last I knew, the iBook version was about $28. I don't know if he's raised the price since then. And the PDF version is roughly around $15. The iBook version is about 580 pages, while the PDF version is about 425 pages. There are 20 embedded or linked HD videos. They're either linked in the PDF or embedded in the Apple version. And there are 50 step-by-step processing tutorials, equipment reviews. So, of course, That makes it, that's what's great about this kind of book, because you can update that more often because the equipment is, again, constantly changing. There's software reviews and a really nice basic astronomy 101 section as well. So I highly recommend that book. As soon as I bought my iPad, like a good 5 years ago, this was the first thing that I bought for it. So we'll begin today with a discussion of wide field astrophotography. And I do want to mention here that all the images, almost all of them, that I share in the lecture today are linked in the companion guide. So if you do want to see these images in maybe a little better detail than I show here, try to use the link in the companion guide and you can check that out. I'm sure some of the links may be a little dated because I try to update those, but sometimes the images just disappear and I can't find them again. So with wide field astrophotography, let's begin with the most basic type, the type that anybody could do on tripod astrophotography. So of course, with tripod astrophotography, the first thing you'll need is a camera. And today you have a couple of choices. First, there's a digital single lens camera, or reflex camera, or DSLR. It's just like a 35 millimeter camera that we saw earlier with the dinosaur, but instead of film, it's been replaced with a CMOS, or a complementary metal oxide semiconductor sensor. So DSLRs are the most widely used camera, I think, still to date. But the DSLR replaced the SLR camera, the old 35 millimeter SLR camera, but now the DSLR cameras are gradually being replaced by the DSLM cameras, which is the digital single lens mirrorless camera. Or I just tend to call it the mirrorless camera because sometimes I can't spit out DSLM. So these do have many advantages over the old DSLR cameras. They're lighter, so they lack the relative bulk of the SLR mechanism. They're good for light tripods or tracking platforms because they're not nearly as heavy. The short flange to sensor distance is better than DSLRs, so it reduces the back focus, which is important for many types of telescopes. And it allows almost any lens to be adapted with the proper adapter. There's no edge shadows cast by upraised mirror or sensor masks like there is with the DSLR sometimes. And they have really good on-screen focusing aids because, again, there's no SLR mechanism. There's no actual optical peephole to look through in the camera. If you do have one, it's a digital version. It's replaced with a digital version as opposed to an optical version where, maybe you're like viewing through the eyepiece of a telescope, more or less. So gradually, the mirrorless camera should replace the old DSLR cameras. They're kind of doing that right now. But I think DSLR cameras still have the edge in probably number of sales, but that's not going to last forever. One of these days, this will get replaced like the 35 millimeter camera did before it. So of course, you're going to need some good lenses. Sometimes the kit lenses they come with are pretty decent, but you're going to want to get some better quality lenses. Like, for example, anything for tripod astrophotography should be between roughly 14 and 50 millimeters. You could use, like roughly, an 8 millimeter lens if you want to do fisheye views of like the night sky, or with like constellations or aurora is pretty awesome. But normally you want to stick anywhere between 14 to 50 millimeter for views of the constellations and Milky Way and aurora and stuff like that. And so here's like another lens, just for example. I forgot that was there. And of course, with tripod astrophotography, you're going to need a tripod, and any probably off-the-shelf tripod will do. They're all pretty much off the shelf. But the really good ones are from Manfrotto or Oben. But if you have kind of an off-market one, like a cheap import, it might be okay. But the really great ones are from Manfrotto and Oben. Those are the ones I highly recommend. And then you don't want to use the shutter button on the camera when doing this kind of photography because you can, move the camera a bit. Even a slight touch will do it. So you want to use a remote switch. This is like an old cable. This is an electronic version of an old cable release for the old 35 millimeter SLR lens cameras. And you can also use a intervalometer. Nowadays, many cameras have them built in, so you almost don't need this accessory anymore. Canon used to have a really nice intervalometer. It was kind of expensive, so most people tend to went with the cheaper imports, which I bought one, but it quickly stopped working. So be careful about that. But there is a great app out there too, where if your camera has Bluetooth technology and you can connect to it, then you can control your camera via your smartphone with the intervalometer app that you can download. I have a link to that in the companion guide. And maybe another concern, kind of backing up here with the camera, is the sensor size. So let me mention that real quick. So most people might want a full frame camera. This is where the CMOS sensor measures 36 by 24 millimeters. That's what we consider full frame because it's pretty comparable to the old 35 millimeter film frames. So that gives you a pretty wide field. But then there's the crop sensors. There's the APS-C from Canon. Those measure about 22.3 by 14.9 millimeters, while the ones from like Nikon, Pentax, and Sony, they measure about 23.6 by 15.6 millimeters. So a little bit wider view than the Canons. Now, you might wonder which brand should I focus on? Years ago, when I first started doing the digital version of this series, when I switched to digital cameras as opposed to the old single lens reflex cameras, I always said Canon. But now it really doesn't make much of a difference. I think, especially Canon and Nikon are pretty equal. I don't know much about the Pentax and Sony cameras, and I don't really see many images from them. It's usually Canon or Nikon are the two big names for either a DSLR or a DSLM or mirrorless camera. So either one should be really, really great. I really can't recommend one over the other anymore. Oh, and I forgot to show the image here of the intervalometer. So some versions are also wireless today too, which is great. Okay, so I'll spend a little bit more time on this because out of all the types of astrophotography that we'll talk about today, this is the one that most people might attempt because anybody could do this. And it's a lot of fun, especially if you get to travel to really dark skies and can take advantage of them. So here are some steps for tripod astrophotography. Number one, make sure your tripod is reasonably level because number one, it's more stable when it's level. And number two, you don't want, crooked horizons. That's not very much fun. So it's great to have your tripod level for those reasons. And so here are the camera settings that you want. This is the most important part. Number one, or A, I guess, is the image quality should always be set to RAW. You can do raw JPEG if you want, where you take a raw image that gets converted to JPEG and you have both saved in your camera. But one way or the other, make sure you take a raw image because if you just take a JPEG image, you lose a lot of the processing ability that you're going to need later. You won't be able to process the image nearly as well with a compressed JPEG as opposed with the raw setting on your camera. B, make sure you set your camera to the bulb or manual setting. Although many cameras can be set to do up to 30-second exposures, and for tripod astrophotography, that's usually pretty much all you need. But if you do want to go longer than usually 30 seconds, you have to be set to the bulb or manual setting. And then the color balance setting should be set to daylight. It'll usually have like a little picture of a sun, like a little sun icon that tells you that's the daylight setting. I've done it both ways, where it's on the kind of the auto setting as opposed to daylight, and it does make a slight difference. It's not a huge difference, but it is, you want to get every edge you can, so make sure it's set to the daylight setting. You want to use an ISO generally of 400 to 1600. Now, the newer cameras, especially the mirrorless cameras, the noise reduction is getting really, really good. So you can probably break this rule a bit. I've seen people easily go up to 3200 or even 6400 ISO and have very low noise issues. So feel free to go beyond 1600 today. But for nighttime astrophotography, you don't want to really use anything less than 400. Then, of course, if you can, make sure your focus is set to manual. Of course, if you can't, then that's not a great camera for astrophotography. But many lenses that are kind of geared more toward this type of photography, or at least the lesser cost lenses, only have manual focus. I have one of those Rokinon lenses that you can only focus manually. So make sure your camera is, or your lens specifically, is set to manual focus, because you're going to have to do the focusing. The autofocus won't do a very good job on fainter objects like stars and stuff like that. And so you also want a lens not in roughly the 14 to 50 millimeter range, but you want one that's kind of fast for most types of tripod astrophotography. Ideally, you want one that's maybe around f2, as we'll talk about later, especially for like aurora photography or even Milky Way imaging. The faster the lens, the better. But f2 lenses that are native f2 can be kind of expensive. There's like versions from Canon out there that are over $3,000, but there are much more affordable versions that are still pretty good. But generally, you want to be in the f2.8 to f4 range, because you want to make sure you bring in as much light, and capture the image as quickly as you can. Keep the exposures down so you avoid trailed stars. And of course, when your focus is on manual again, make sure you focus on a bright star first. Like, during the summer, you can use like Vega. It's usually very high overhead, so the scene is good. But if you don't have a screen on the back of your camera that can tilt out, it can be a bit difficult to see. But you can focus from other devices too, like a laptop or even maybe a tablet, to get in a bit more comfortable position. But either way, you want to focus on a bright star. And oftentimes you get lucky, because when you do focus on a bright star, when the focus gets really good, fainter stars will pop into view, because normally when the fainter stars are out of focus, they get dimmer, so you can't really see them. But if you're focusing on a bright star, then other stars start popping into view on your screen. That means the focus is getting really, really good. So that's one kind of hidden technique, kind of secret technique that you can use. And obviously, frame your shot. This might be a little more challenging for a mirrorless camera, because again, everything is digital. There's no optical component to look through. And the mirrorless cameras tend to use up a lot of batteries. So maybe one thing to add to here is make sure you pack extra batteries. But today, with framing your shot, because you can have huge storage cards, maybe take a few sample images to check your framing. You can just kind of go off the screen on the back of the camera, but you can also just again take many short images and see what the framing looks like. Because back in the old film days, you had maybe up to only 36 images you could take. Today, you can take thousands. So why not take a few sample images just to see how the framing looks? That's what I generally do. And then you can start taking exposures from roughly 10 to 30 seconds. Again, this is for tripod astrophotography. So this is what you want to do to avoid getting trailed stars. But one thing you can do is, again, a little calculation. Is you can use what's called the 500 rule, which was pictured right there, but I didn't see it. So there are like updated versions of this you can look for online, but I decided to stick with the general version here for for time's sake. So with the 500 rule, you basically divide 500 by the focal length of your lens, and that tells you the maximum exposure in seconds. So let's, again, make the math easy. Let's say you use a 10 millimeter lens. That means you can take images up to 50 seconds without any trailed stars. So it's just a general rule to avoid trailed stars. But of course, if you do star trails, you can do a series of 60-second or even 2-minute exposures. But I usually recommend doing, roughly 60-second exposures for star trails. But again, maybe a little more on that later. Because again, this time your goal is to get trailed stars. And lastly, make sure you look at the histogram graph on your camera, because you always want to expose to the right. So oftentimes what we photograph is very dark, maybe except for bright aurora or the Milky Way, but you don't want the peak of the histogram or this curve here slammed over to the left. So make sure you get it roughly right about here, not way over here to where it's going to be overexposed. But again, kind of that sweet spot, which is a bit right of left. So not slammed to the left, but a little bit to the right. So exposed to the right. Alan Dyer goes in a lot more detail on that in his iBook. So be sure you check that out. So let's go ahead and look at some samples here of some tripod astrophotography. Now, the one on the right here is one I took at the 2001 Texas Star Party with my old SLR camera using what was called Kodak LE 400 film, which was some pretty good stuff back in the day. And this is a piggyback image on my old 10-inch LX200. So I put the camera on top of the telescope and use the telescope's clock drive to take the 60-minute exposure. Again, with film under the dark skies of West Texas. But look at this one here that I took back in 2010 from the Okie-Tex Star Party. I used an old Canon 550D or T2I with a Canon 24 millimeter lens at f2.8, and I took a 25-second exposure at ISO 6400, which was a little noisy. But I wanted to kind of see what I could do with a digital camera compared to the old film camera. But again, this is only 25 seconds, and this is an hour because, again, the digital sensors are much more sensitive than the old film that we used to use back in the old days. And of course, you can do much more general constellation pictures. And I'll show you a lot that I found online that I've liked over the years. I would use all my photography, but I'm like my own worst critic, so I don't like to show a lot of my stuff. But I've always been fond of this image. This was actually taken at a Greek star party in Greece, of all places. So it's called Big Bear above Mount Parnon, taken with a Canon 500D or T1I. And I believe he used a program called Star Spikes to get the spikes in the star. So the spikes are artificial, and I think the brightness of the stars is also exaggerated. I don't believe he used any kind of filter. At least I didn't make any note of it. But it's a really neat effect too. So you can use kind of programs like that to give you these artificial stars for, of course, artistic purposes. But I don't know. I've always been fond of this image of the Big Dipper. Now, this one's from the Nikon website. It's no longer actually on their website, but I still have the link to the website in the companion guide. So in this case, this is an image, of course, of the constellation Orion with a Nikon D75 and a 58 millimeter f2.2 lens. But in this case, he used a Kenko soft-on spec A filter to give the brighter stars a bit of a bloat here. So the stars are a bit bloated when photographed through the filter, which is a really cool effect to really emphasize the brighter constellations like Orion or even Ursa Major and Scorpius and stuff like that. So you can use these filters too to get these cool effects. And oftentimes you can photograph conjunctions of the moon and planets. So here is a waning crescent moon with Venus. And with this type of astrophotography, especially if you want to get featured on websites like Space Weather or of course Astronomy Picture of the Day. I've been featured 3 times on Space Weather, but never on APOD because that's really hard to do. But they say if you want to get featured on websites like that, it's really important to have a really interesting foreground. So notice the really cool foreground here, this little pier, and with the moon and Venus, way off in the background. And again, this is only a 1 second exposure at ISO 640. So this type of astrophotography is really easy and really rewarding too. If you got, again, a 8mm lens, you can do stuff like this. This is maybe, again, where you want a more fisheye type lens. And so you can do a 22-degree moon halo. So moon halos like this are caused when the moonlight refracts off ice crystals in a thin veil of cirrus clouds, as you can see here. So sometimes the thin clouds during the winter like this can be really helpful because you get this cool halo effect around the winter hexagon here. And again, this is only a 25-second exposure at ISO 400 with an 8mm film. And so you could make an argument this is more weather photography than astrophotography, but I think this still counts. Sometimes you get these cool sun pillars. I've seen several around West Michigan, but here's one at Cerro Paranal in Chile. So again, you get sun pillars like this. They basically develop as a result of ice crystals slowly falling through the air and again reflecting the sun's rays off of them. So they do it in a nice vertical fashion. So you get this shaft of sunlight. And again, these only occur around sunrise or sunset. And it really helps to have the clouds that give you this nice contrast. So, maybe not technically astrophotography, but hey, it still counts. And you can make an argument that maybe this isn't astrophotography either, but here's an extraordinary a solar halo. I mean, this is just a remarkable image because it shows basically every type of atmospheric phenomena you can get with this type of image. So we again have a 22-degree sun halo, a sundog, an upper tangent arm, a circumzenithal arc, and again, all these patterns are generated. The sunlight is reflected and refracted in flat, six-sided water ice crystals. So it's just a remarkable image. And again, you have to be in the right place at the right time to get this. But if you have your Canon camera with you, or even Nikon, in this case, a Canon 5D Mark III with a 24mm lens, again, this is a very easy form of astrophotography. The exposures are very short. Pretty much any tripod will do. And of course, with tripod astrophotography, you can try to capture the elusive green flash. This is where you definitely want to exceed the lens type I discussed earlier because you want to get kind of close to the sun on this at sunset. So you can see he used a 300mm lens at f8. Probably this could be a series of rapid images to capture this, or he recorded the video and just did a capture from the video to get this. Because again, the green flash happens very quickly. And again, this occurs because the atmosphere causes the light from the sun to separate or refract again into different wavelengths. And again, the green happens very quickly. You could even find lots of videos of this on YouTube to see it how fast it happens. Now, you only have a few more years to do this, but you can capture the International Space Station passing high overhead. These are very likely airplanes here crisscrossing in the sky. And in this case, you can see it's 11 10-second shots. You can try to record one image of the space station, but usually it takes several minutes to pass overhead. So that's what causes the gaps. So you can probably almost count 11 different gaps here because the space station moves a bit between each individual exposure. Or again, you can try to do one long exposure, but you know, sometimes the noise tends to overwhelm the image. So again, this is with the 16 millimeter f4, and you combine several images together. Now, this was a part of a time lapse movie that the photographer put together. You can check that out on the website linked in the companion guide. And in one of the images of his time lapse movie, he captured this bright meteor. So, of course, if you're lucky enough at the right time of year, like during the Perseid meteor shower, you can capture meteors, on images like this. So here we have a Canon 6D Mark II with a 24 millimeter lens at f2.5, and each individual image is apparently only 8 seconds. Isn't that amazing? Just 8 seconds for that at ISO 3200. And he got really lucky and captured this really great bolide on his image. Now, here's an area where, again, you want a really wide field of view. So this is with a 14 millimeter f2.8. And again, it's nice to have a foreground like this, but most of us aren't quite that lucky. So this is the zodiacal light at La Silla in Chile. So the zodiacal light is basically sunlight reflected off dust in the plane of the solar system. It's most likely dust from, comets and asteroids, but there's been a suggestion some of the zodiacal light, or maybe all of it, is from dust that's been ejected by Mars. And I don't know how exactly Mars can give off all that dust, but again, I think it's still more likely it's from asteroids and comets reflecting sunlight in the plane of the solar system. So whenever I do go out west to a star party, I do see this there. I've never really seen it from Michigan, although I'm sure you can do it from upstate or even the Upper Peninsula, but I've never seen it from there. And he did capture a really faint meteor here during his roughly 3-minute exposure. So again, a really cool image of the zodiacal light, kind of a natural form of light pollution. Now again, every roughly 10 years, you get a bright comet. And this is the one that just makes me depressed every time I think about it, because we didn't get to see this at all from West Michigan. I mean, it was briefly naked eye from the Northern Hemisphere, but it really put on a fantastic show for those of you in the Southern Hemisphere. So here's Comet McNaught, just incredibly bright. From all accounts, it looked very much like this visually, but I can't attest to that. So this is with a Nikon D200 and a Sigma 20 millimeter lens at f1.8. So again, a very fast lens to capture the fine detail here before it gets blurred too much by the atmosphere. And again, you can see this is a combination of 30 64-second images at ISO 800. And this is from Australia. Of course, we just wrapped up 2 great eclipses here in the US, but here's another eclipse over, again, La Silla Observatory back in 2019. So if you're going to travel to, say, Spain in August of 2026, perhaps you can do images somewhat like this, just maybe not with the observatories in the foreground, but here we have just a 1/3 second exposure at ISO 100 with a 24 millimeter lens and a Sony camera. So yeah, those Sony cameras seem to do a pretty good job in this case. Now, we're still around solar minimum as we record this, so perhaps you'll get lucky. There'll be a strong solar flare or a coronal mass ejection, and you can run out and capture the aurora. So between Milky Way astrophotography and aurora astrophotography, these are the types that most people do. So this is the one maybe even the ordinary non-astrophotographer would want to do. So if you do want to do this, again, get yourself a good DSLR or DSLM camera with a fast lens. It can be, again, anywhere from roughly 14 to 50 millimeter, but wider field is often better. But you want it to be fast because the aurora is dynamic. It's constantly changing. So you want the fastest lens you can afford. So here's a really great image with an f2, which captures the aurora fairly sharply. And again, just a 4-second image at ISO 2500. So again, just a beautiful image that many of us can take, maybe not with the nifty foreground. This is from Healy, Alaska, but still, you could do pretty great aurora photography when it does become visible from your area. And then we mentioned star trails a little bit earlier. So here's a great star trail with these pretty cool petroglyphs in the foreground. So again, it helps to have a really cool foreground. It could be a tree or maybe some kind of old building in the foreground. But again, you want a good foreground often with this. So this is with an old Canon 6D with a zoom lens set at 10 millimeter and f4. You don't really need a fast lens to do this. So here you can see the photographer did 74-minute images at ISO 400 for a total of 4.7 hours. And then he did 30-second images for the foreground and processed those separately and then combined them together in like Photoshop. So this is one of the things that Alan Dyer teaches you how to do in his iBook. And so he used programs like Star Trails to process the background image, and then Star Stacks to do the star trailing as well, and process the foreground and the background. So there are freeware out there besides Photoshop, again, like Star Trails and Star Stacks. So that was used to take this image here. So those are some examples of tripod astrophotography. But if you get the bug and you want to do more of this, you're going to want to take, of course, longer exposures than a tripod permits you to do. And that's where you can start doing piggyback astrophotography. And again, that's how I took that image of the Milky Way back in 2001 at the Texas Star Party. So I used a Meade, but of course they don't exist anymore. But here's a Celestron Schmidt-Cassegrain with a piggyback mount that bolts onto the existing hardware of your telescope, and you can put the camera on there and basically borrow the telescope's clock drive. Of course, it has to be mounted equatorially, either with a wedge with a fork mount here, or of course with a German equatorial mount. So here's an Astrophysics Mach 1, which is the mount that I have, with a camera piggybacked on a nice refractor here. So, of course, there are other needs for this type of guided wide field imaging. As mentioned, you're going to need a piggyback mount. And there are plenty of places to get those. So it's not hard to find one. You're going to need a dovetail plate, most likely, for your Schmidt-Cassegrain, or possibly your refractor, or even a Newtonian. So those are available from companies like Lossmandy or ADM Accessories, especially with the ones mounted on a fork mount, like Schmidt-Cassegrain's mounted on a fork mount. You might want a counterweight system. Or if you start using, long telephoto lenses that are very heavy, or especially small refractors, you're going to want some mounting rings. And if you do get mounting rings with a refractor, you definitely want a counterweight with a fork-mounted telescope, or with a German equatorial mount, you just add the regular counterweights to your system to balance it properly. And if you do use your telescope for astrophotography, as opposed to like lenses or telephoto lenses, you're going to want to get yourself a T-ring. These are widely available at local camera stores, or of course you can order them online. So these basically replace the lenses, and then you use adapters like T-rings or T adapters to thread on to the T-ring. So again, like these threads here, for example, thread on to the inner part of the T-ring there. So there are plenty of these adapters. This one, for example, is for a Schmidt-Cassegrain. This one can be used for a refractor and a Newtonian. So it depends on the type of telescope you have. And of course, You can get yourself some really nice telephoto lenses, but many of us just buy a small refractor because honestly, it's cheaper to buy a really good small refractor as opposed to some of these telephoto lenses. But I know many professional photographers that have access to these lenses, through their job, and they use them for astrophotography. But again, a small refractor is probably a little cheaper, but this gets you in the 600 to even 400 millimeter range. So here are a few examples. Again, some really pretty ones that I found online. So here's Comet Lemon and 47 Tucana, the globular cluster, and the Small Magellanic Cloud. So the comet just happened to pass by these two objects, and this photographer captured it. So again, you can see this is with a Canon 1000D and a 135 millimeter telephoto lens, and he took 25-minute images and stacked them together. Now, what a lot of people ask is, why can't you just take one 5-minute exposure and stack them? Just copy them and stack them. It's because every camera has noise. So if you try to stack copies of a single image, you bring out the noise, but the noise is random. So that's why you take a series of images to combine them together to reduce the noise and increase the signal, because digital imaging is a fight between the noise and the signal. You want the signal to overwhelm or dampen the noise. You don't want the noise to overwhelm the signal, because then the image just looks terrible. So that's why we take a series of images like this. And the really great advantage is some annoying bright plane, or of course now today Starlink satellites. If they happen to pass through some of your images, you can just discard those images and stack the rest that are good. All right, so there are other ways to do guided wide field imaging besides piggyback astrophotography. If you really want to do this on the cheap, save yourself some money, build yourself a barn door tracker. I know many people have done this just for the experience of building one to try it out and see how it works. But these are great. These are often hand operated, kind of like this one. So you basically turn this little dial like every few seconds or so, like every 20, 30 seconds or whatever. It varies by the style that you build. And that basically acts like a clock drive, an auto, a motorized clock drive. So you can see there's like a laser pointer on this one to do the proper polar alignment. So it's tilted at the angle that depends on your latitude. And you have this end point toward the North Celestial Pole. And then you can, again, move the dial here and crank it. I've seen motorized versions out there. So again, if you're a do-it-yourselfer, you can build one of these little handy gadgets. Now, I can't find too many images from barn door trackers online, and I've never built one myself, but here's a decent image of the Orion Nebula with a Nikon D7000 and a Nikkor 180 millimeter lens. So again, he took 172 30-second images for an 86-second exposure. I bet with more modern processing techniques, you could get a much better image out of that today. But this is still a pretty respectable image of the Orion Nebula. But of course, what most of us do is we buy these star trackers that have become very popular over the past 10, 15 years or so. So here are many of the star trackers that you can go out and buy today. Here's the AstroTrack 360. This one's more of a work of art than anything. It is really expensive, but man, is it a beautiful piece of machinery. But it can hold up to 22 pounds, comparable to a really good German equatorial mount. But boy, this thing is beautiful. So here's an example of an image with the AstroTrack. So this is the Eastern Veil Nebula, or NGC 6992, visible in Cygnus. This is with a Canon Sony Alpha 7R mirrorless camera and a Canon 500 millimeter lens at f 4.5. because this time you don't want it to be too fast because then the sky background gets too bright. And this is a challenging area to image too because we're looking right into the disk of the Milky Way. So there's just lots and lots of stars, and that can be difficult to process again sometimes. So this is only 33-minute exposures taken with an AstroTrack. Here's one from Explorer Scientific called the iExos 100-2. This one is basically a small German equatorial mount, but again, it's kind of classified as a star tracker because it's so small, and it holds about 15 pounds. So again, it can do small refractors, but it's more meant for cameras with lenses or especially telephoto lenses. Nothing too heavy. So here's an example with the one from Explorer Scientific. This is the famous Elephant Trunk Nebula. The actual elephant trunk part is kind of right here, kind of hanging down from the top of the image there. This is with a Nikon D810A, which is one of the rare cameras specifically built for astrophotography, or at least it's a regular D10 with a special filter put in for astrophotography. And you can see this is with a small refractor, in this case, an old Meade 70mm refractor with 36 3-minute images. Again, very, very good image. Another popular one is the Kenko Sky Memo. This is the Sky Memo S, which holds about 11 pounds. And this is a smaller version, the Sky Memo T, that holds about 7 pounds. And here's an example of an image with the Sky Memo, the famous Rho Ophiuchi region. Many astrophotographers just love imaging this region because it's so colorful. There's so much going on here. Of course, you got dust in the Milky Way. You got this kind of region here with the star Antares, this nice blue reflection nebula, a little bit of emission nebula, the globular cluster M4. So there's just a lot going on here. And again, this is with a Canon 6D and a 200mm lens. Now, some of the really popular ones is the Ioptron models. I have the old Sky Tracker that looks like a little black box. The more modern versions are a bit sleek. So these are kind of the earlier versions of star trackers that are still really, really good. This one holds about 6.6 pounds, so not really meant for refractors. It's meant more for just cameras with wider angle lenses, probably not even much in the way of the larger telephoto lenses. So it's with these you can do tracked images of the Milky Way. So here's my image of the Milky Way from a more recent Texas star party in 2016 to be exact. So this is the Milky Way rising from the 2016 Texas star party with my Canon 600D. It's not an Astro modified one. And I used a Rokinon 24mm lens. I stopped it down to f4.4 because the stars were a little funny on the edges at f2 or f2.8. And again, I use the older Sky Tracker with that looks more like a black book, a little black box. And this I did a whole series of images to kind of bring on a more high dynamic range. It's only, again, 7.2 minutes, so not a lot of effort to take the image, but a bit more to actually process it. A bit more fancy is the Ioptron Sky Guider. Again, it kind of looks like a little German equatorial mount in this configuration here, but you don't necessarily have to use the counterweights, but you can do this if you're using large telephoto lenses. And this one can hold up to 11 pounds. So again, it's more capable for telephoto lenses. And here's a great image of the large Magellanic Cloud. We saw the small Magellanic Cloud earlier, so I have to show the large Magellanic Cloud, taken with the Sky Guider using a Canon 6D and 135mm lens. If you like well-machined tools, here's the Losmandy Starlapse. And this thing is pretty beefy. It's kind of heavy, but it can hold up to 30 pounds. And like all the other stuff from Losmandy, it is well machined. I mean, it's just, again, very, very beautiful instrument. And it does have a pretty large capacity too. This thing exceeds many German equatorial mounts. So here's another image taken with the star lapse of the Pleiades with a Canon 5D Mark II and a 200 millimeter lens, or at least a zoom lens set at 200 millimeters. Another type are the Star Adventure series. There's the really popular 2-eye Star Adventurer. This can also hold about 11 pounds. And this thing has been a big seller. So among star trackers, this is one of the most popular. But there's also the GTI, which is very good. I have one of these. It's again like a little German equatorial mount. And the one advantage this has over all the others is this has go-to capability. So you can use a smartphone or a tablet to control it and point it at targets in the sky. So it basically, again, it's a small German equatorial mount, but it's marketed as a sky tracker. So this thing has become very popular as well, but it also only holds about 11 pounds. People were hoping it would have a bit more capacity than the TI, but nope, it is also 11 pounds. And so here's a nice image with the Skywatcher Star Adventure, the 2-eye. I don't actually have any to share with the GTI. At least I didn't put any in. And this is by our friend Alan Dyer, the author of that great iBook, with a Canon 5D Mark II and a 50 millimeter lens of the kind of Cygnus region of the Milky Way. You can see the North American Nebula, a little bit of the Pelican, and a small part of the Great Rift in the Milky Way here. Again, a very hard area to image. Takes a really good lens because it's so packed with stars. Now, the first ones to come on the scene were from the company Vixen. This is their newer model, the Polaris U. This one doesn't have a large capacity, but again, you can use it with a counterweight as shown here to get a bit more capacity out. But in its more natural state, it holds about 5.5 pounds. It can also be set up to do time-lapse images. So that's a bit unique amongst most of the star trackers. Is again, this can be configured to do like a time lapse where it slowly turns so you can get this pan effect during your time lapse movie. So here's a really great image with the Polaris U. This is Comet Lovejoy Q2 because there have been lots of Comet Lovejoys. So this is specifically Lovejoy Q2, and of course the Pleiades and the California Nebula in GC 1499 with a Canon 85 millimeter lens on a Canon 5D Mark II with 34 3-minute images. So again, it helps to have the comet in just the right place to get a really scenic view like this. And finally, we have the one that kind of started the Star Tracker phenomena, this Star Tracker popularity, is the Polaris Star Tracker. This is the first model to come out around 2009, 2010 or so. And then, of course, other companies started coming out with their own Star Trackers. But this is the first and the classic. So it only holds about 7 pounds. So it's only for, cameras with, wider angle lenses, but it's very small, very portable. You can take it almost anywhere. And so again, it has the designation of being the first. And again, here's another wider image of the Rho Ophiuchi region using the Vixen Polaris and a Canon 6D and 135 millimeter lens. So now let's move on to prime focus deep sky astrophotography. Now, you can do prime focus deep sky astrophotography with a DSLR or DSLM camera, the ones we've been talking about. But nowadays, many people are moving away from those cameras and using the ones specifically designed for astrophotography. Now, these have been around for a long time, of course, we had CCDs come on the scene in the mid 90s, and they only got better as they went on. But now CCDs have been pretty much replaced by the CMOS sensors, the same ones used in your DSLR or DSLM cameras. So there are several manufacturers out there, but kind of the two most popular ones, I think, are either from ZWO or QHYCCD. They're probably going to change their name at some point, I imagine. But here are almost all the cameras available for deep sky prime focused astrophotography from ZWO. One of the really popular ones initially was the ASI 294. That was a very popular camera because it had again, a pretty good resolution, 11 megapixels, which is still pretty good by today's standards. The sensor size was a bit small by today's standards, but still pretty decent resolution. And it has a high quantum efficiency. So what that is, quantum efficiency, or just QE for short, is basically a measure of the effectiveness of an imaging device to convert the incident photons into electrons. So, for example, if a sensor had a QE of 100% and was exposed to 100 photons, it would produce 100 electrons of signal. So you could say, the larger quantum efficiency, the more sensitive the sensor is. So you might think, well, you want something with a high quantum efficiency. And of course, many people do. But I've done great work with an ASI 071, which, according to this, I think that's correct, has a 50% quantum efficiency and a bigger sensor than the 294. But probably the most popular one today of out of all the ZWO cameras is the ASI 2600. So if you're looking for your first dedicated astronomical imaging camera, this is a really, really good one to get. It's a really good resolution, 26 megapixels, or with roughly a 6248 by 41 76 pixel array with a kind of a crop sensor type size sensor, and it has a 91% quantum efficiency. And they can be cooled to minus 35C, but a lot of people do minus 10 degrees Celsius today because the noise level is so low on these newer cameras. It's almost not 100% necessary anymore to fully cool the camera, because normally we only went to like minus 20, but the electronics in these cameras aren't nearly as good as the much more expensive ones, like from the old S-Big cameras. So usually in the summer, you could never cool these cameras to minus 20 Celsius anyway. But usually minus 10 is pretty doable under most conditions. And that's what many imagers do today. They just cool it to about minus 10 because, again, the noise level is so good. So there are several types, but again, this is the most popular. But if you do want a full frame camera, then you can check out the ASI 6200. I know some of our members have one of these and have done some very good images. It's a high resolution, again, large pixel array, and a really good quantum efficiency. So for full frame, this is a good one. If you don't want to spend quite as much, you can get the ASI 2600. While ones like the 071 or the 294, they can be found for very low costs used today, unlike Cloudy Nights or Astromart or something like that. So here are the ones from QHY CCD. I know some of our members boast about these because, again, of their low noise levels. We're currently looking at this one here, the QHY 600, for a replacement for one of the cameras on our remote telescope in Arizona. So this one, again, it's a full frame camera, but kind of one comparable to the ones we talked about, the ASI 2600. It's probably around the 268 model or the 367 model. They have ones that are a couple that are very comparable to the one from ZWO. But QHY is a really good too if you don't like the ZWO model for some reason, but they're both very, very good. Now, you can see many of these are available in either monochrome or both color and monochrome. Now, of course, there are filters you can get for the color cameras, but if you really want to get into more serious imaging, you can use a monochrome camera because the detail in your images is much better because of the way color sensors work. You know, there's like a row for red color, there's a row of pixels for the green color and a red of pixels for the blue color, and so on to create a color image. But with a monochrome filter, it's all monochrome, so no colors are being discarded or ignored, and it's much higher resolution to take stuff in monochrome as opposed to a color camera. But a lot of people can't tell the difference anyway. But if you do a lot of monochrome stuff, you're going to want to get yourself some good filters. And I won't spend a whole lot of time here, but again, to do the color images, the more natural color images, if there is such a thing, you know, natural, you can use the LRGB scheme, where the L is the luminance filter or a clear filter. It's basically a filter, in a sense, to keep dust off the sensor when you're taking an image, you know, to protect the sensor. And then you can do the RGB images to create a full color image. Or you can get into narrowband imaging with H alpha, oxygen 3, or sulfur 2. And of course, that's a little more advanced type of imaging, but still, H alpha in like O3, for example, are really rewarding in more light polluted areas. I'll show you an image from one of our members that lives in a pretty light polluted neighborhood, like many of us do, and he does pretty much exclusively narrow band imaging from his small backyard observatory. So these filters are widely available from companies like Astrodon. They're the classic, but Don Goldman doesn't own Astrodon anymore, and some people have said the quality has slipped a bit since then. But the ones we have for our remote telescope were from the original owned Astrodon, and they are very good. And then there's Antlia, which are a little more affordable, and ones from Astronomic or Batter or Chroma. So there are many, many filters out there. So again, you can check prices and find the ones that work best for your setup. Now, if you do want to do prime focus, deep sky astrophotography, don't start out with a long focal length telescope like, say, a Schmidt Cassegrain. You want to start small aperture, wide field. So, of course, with wide field telescopes, the best and the ones that have the most choices out there are, of course, refractors. So if you really want to do this type of astrophotography, start with a wide field refractor. And there are, again, many choices out there today from companies like ASCAR. They have a wide variety of apertures available. I'm just showing a few samples here. They go down from roughly 50 millimeters up to like 6 inches. There's Astrotech from Astronomics. They again go from roughly 60 millimeters up to 152 millimeters. Maybe you would say this type of telescope, this long refractor with a large aperture, is not necessarily wide field imaging, but you know, compared to some telescopes, it is. But you know, I'm mainly talking about the smaller models here that are very light and can be well supported on most mounts. Now, of course, ASCAR, Astrotech are, you know, mainly made overseas. The optics, I think, of most teleview scopes are, but if you want one that's, again, finely crafted, you know, well built, you can get yourself one of the classic televiews. I hate to call them classics, but they are excellent, though. They may be a little older than some of the newer models that come on today, but they are extremely well built. And again, you're supporting an American company. They might get some of the stuff overseas, but they assemble them in Suffern, New York. So televiews are awesome. And again, for kind of Chinese imports, there's Sharp Star. There doesn't seem to be as many Sharp Star telescopes available. This is actually all of them today. So it looks like they might be phasing out the refractors. But the company that owns Sharp Star also owns ASCAR. So maybe they seem to be focusing more on the ASCAR models as opposed to the Sharp Star refractors. The Sharp Stars all seem to be going to reflectors that I'll show you here in just a second. But out of all the wide field refractors, this is actually the one that I own. And this is a really, really good one. It's a cute little booger. It is very small, but it is great for wide field imaging. And like many of the refractors I'm showing you, they all mainly have dedicated field flatteners too, because it's really important to have a field flattener because not only does it flatten your field, but they're usually focal reducers as well that give you a wider and even wider field of view. So I have a field flattener focal reducer for this one too that makes it more of a true like astrograph, which is a telescope especially for astrophotography. And then on the high end are ones from Stellar View. I actually own a 130 millimeter or 5-inch Stellar View that I've used for the past two eclipses and also for some deep sky imaging. But they do have smaller ones, roughly down to again roughly 60 millimeters up to a good 6 inches, 150 millimeters or so. So again, the big ones like this one especially are very expensive. These aren't quite as bad, but compared to the imports like from ASCAR and Sharpstar, these are much more expensive, but a bit higher quality. And again, they are assembled in the US. Then there's William Optics. I know the Red Cat telescopes are extremely popular. So these are like the Red Cat. I think this one's called more specifically the Ultra Cat, but they're kind of based on the Red Cat original version. And then there's the Pleiades model, which has become very popular from William Optics. And again, they make many more than I'm showing here, but I can only show you a few at a time. So let's look at some sample images with these wide field refractors. Here's one from one of our members. This is a pretty recent image taken just this past winter from member Tim Kurtz. This was actually taken from Arizona Sky Village, where our remote telescope is located, and his father owns a house there. And of course, he goes to visit and does some astrophotography. So here's a really excellent image of the Horsehead Nebula with a ZWO ASI 071. So yeah, it may have a low quantum efficiency, but it takes really good images. And here he used an ASCAR 71F flat field refractor. I don't know if he used a focal reducer. He didn't mention it specifically. And this was taken with a ZWO AM5N harmonic mount that I'll mention briefly later. And so again, he took 160 2-minute exposures for a total of 5 hours, 20 minutes, processed in programs like PixInsight and stuff like that we'll mention later. And another member, Pete Mumbauer, took this image of the Andromeda galaxy from the Kalamazoo area from his backyard observatory. And here he used an old-fashioned camera called a CCD, which again has been replaced, but Pete has since upgraded to a CMOS camera, but this was taken with an ATEC 383L CCD camera with the previous generation of the Sharpstar. Now they're up to the 3, which is the one that I have, but he has the Sharpstar 61 EDPH2 with the flattener reducer. And he used a nice high-end mount, an Astrophysics 1100 GTO. And of course, this is a monochrome camera. So he did images through luminance, red, green, and blue filters for a 14-hour equivalent image of the Andromeda galaxy. Now, I mentioned earlier we have a member that lives in kind of a light polluted area that does exclusively narrowband imaging, and that's Dave Garden. But he did this along with his son Matt. And so earlier we saw a kind of more regular image of the Elephant Trunk Nebula, but here's a narrowband image of the Elephant Trunk Nebula. He used a full frame camera, a ZWO ASI 6200 Pro, with a very high end wide field refractor, a Takahashi FSQ 106 EDX3. We have one of these in our remote telescope as well, but with his Takahashi, I'll tell you, even without a focal reducer, this is the flattest image or the flattest telescope ever. I mean, we tested some of his images once, and it has like it was like 3%. I mean, so I hope if he does ever sell that, either the club or I will buy it, because man, that thing is flat. So some Takahashis are better than others, and we've had some issues with the one we have with the remote telescope. And so you can see this is with the Losmandy G11 through H alpha, O3, and S2 filters for just 4.5 hours, which is relatively short compared to many exposures you see today. Now, what if you want a little more aperture? You don't want a small refractor with a small aperture. You want to get something a little bit bigger. So you can get yourself a really good Newtonian reflector. So there are several models out there, but you don't quite have the same choices, the vast array of choices as you do with refractors, because they are not nearly as popular, but you can take some really good images with a good fast Newtonian. So there's ones from Apertura. Still got to work on that pronunciation. They have ones ranging from 6 inches to 12 inches. They have the nice Carbon Star version with a carbon fiber tube, which is great for thermal expansion properties. It doesn't expand as much or contract as much during the course of a night as the temperature changes. So many people do recommend the carbon versions as opposed to the old aluminum tubes. So Apertura has some nice ones available. Again, Astrotech from Astronomics. I have a modified version of the old 8-inch that I bought years ago. I replaced the Crayford focuser with one from Moonlight focusers. That's much, much better. And I replaced the knobs on the back with something that's easier to collimate than what they have. So if you do buy one of these, like the 8-inch here, it does require some modification to really bring out its full potential. So it does need some work. But they do have this truss style Newtonians that are more designed for astrophotography, even though these are strictly billed as imaging Newtonians, but they require some work out of the box, frankly. This one probably does not to a degree, but you probably could. So these range from roughly, again, 6 to 12 inches. There's a pretty big Newtonian, but that'll require a pretty hefty mount. And again, Sharp Star, as I mentioned, they seem to be getting away from the refractors and focusing on the Newtonian specifically for Sharp Stars, while the ASCARs are now the kind of refractors from that same company. So those are all carbon tubes with I'm not sure if the colors are different types or just different colors. I don't recall specifically, but these are very, very fast, like F2 or F4 or something like that. And with all these fast Newtonians, you're going to need a coma corrector too, where, coma is where stars look like little comets on the edge of the field of view. So, but that's easily corrected with a coma corrector, and they're not terribly expensive either. And then finally, there's a Skywatcher. They also have a series of Newtonians kind of geared toward imaging. Some are kind of small, like the 6-inch, but they do have ones up to a 12-inch too. But again, those require a really hefty mount. So look at a few sample images. This is an old one by me. This is with my modified Astrotech 8-inch f4 Newtonian that does have a coma corrector. And this is from the 2010 Okie Tech Star Party again that I mentioned earlier. And on this night, I don't recall the exact date, but it was in October 2010, Comet Hartley 2, which was kind of small and faint, passed near the famous double cluster in Perseus. So back then I had a Celestron C Gem that I've since sold and upgraded to a Astrophysics Mach 1, a very good mount, by the way. But here's a great one from Pete Mumbauer, more recent image, taken with this newer camera, an Agma. I don't really mention them too much here, but they're kind of new on the scene. But they're kind of an alternative to ZWO or QHY. So this is with the Agma excuse me, 26 color camera of M17, the Swan Nebula, or the Checkmark Nebula, or the Horseshoe Nebula. It has a lot of names, this one. So he used a modified 12-inch f4 Newtonian, but again, that's a big telescope, so he puts it on a big mount, an Astrophysics 1100 GTO, very high-end mount, like the Ferrari of telescope mounts. And I believe this was originally a GSO telescope, but he replaced the aluminum tube with a carbon fiber tube for, again, better thermal properties. And here's another image from Pete, our ace astrophotographer in the Kalamazoo Astronomical Society. Here's the Triangulum Galaxy M33. And this was from a darker area in Kalamazoo County, but still within his backyard, still a bit of light pollution in the area. And again, you can see this with his older CCD camera. And this is back before he got the astrophysics, and he had a Celestron CGE Pro, which was still a very good mount, but still not quite as steady as the astrophysics. So again, yes, a good mount is important. And this person took that to heart. I took this picture at, I think, the 2005 Winter Star. No, wait, 2011, because I've been to 2 Winter Star parties, and this is at the 2011 Winter Star parties. So here's like a 60 millimeter Takahashi, probably weighs all of maybe 10 pounds, on an old Paramount ME that holds up to 200 pounds. So this person takes steady mounts very seriously. Now, do you have to go this overboard? No. So let's take a look at some really good German equatorial mounts for this type of astrophotography. And I do really recommend either a German equatorial mount, especially for larger telescopes, like a big Newtonian or Schmidt-Cassegrain. But there are many German mounts that work good for small refractors as well. But we'll look at the harmonic mounts real quick as well. So with Celestron, they have the advanced VX mount that holds about 30 pounds. There's the CGEM 2, the successor to the mount that I once owned, that holds up to 40 pounds. The one Pete used to use is the CGX, that holds up to 55 pounds. And now they have the CGXL, kind of a beefier version that holds up to 75 pounds. So the VX is what you want for maybe a small refractor, because sometimes with Celestron and other companies that import these, I tend to divide the stated weight capacity by half. So if they say it holds 30 pounds like this one, I tend to say it would do really well at 15 pounds. So that would put it at, again, a kind of smallish refractor. With the higher end mounts, go by what they tell you. They can even exceed that. But with kind of the more imports, I would be a little skeptical, on the stated weight capacity. That's what I noticed with my CGEM. It was supposed to hold roughly 30 pounds, I think, the original version, but it got a little shaky when I had like a 9¼ inch Schmidt-Cassegrain on it. So I personally tend to take it with a grain of salt. Now, there are several models from Ioptron. A couple of them are not German equatorial mounts. There are these center balance mounts like this one, but I decided just to group them in here with German equatorial mounts. So they have this CEM 26 center balance mount. You can see the telescope would be on one end and the counterweight's on the other, while the balance is more centered on the tripod and the mount there. So I've seen some of these in person, but not a lot. So they're not really widely available or widely seen out there. Maybe you know someone that has one, but I haven't seen that many to really see if they make a huge difference. But um, usually the number is the weight capacity. So this one holds about 26 pounds, but only weighs 10 pounds. So that's pretty good. It's very light, but has a pretty good capacity. Here is a more traditional German equatorial mount from them, the GEM 28. This again holds 28 pounds, while the center balance mount, the 40, holds 40 pounds. You guessed it. And then they do have a German equatorial mount that holds 45 pounds. And then the bigger mounts, they have this large center balance mount that holds up to 70 pounds. And I forgot to write down the capacity of this one. I believe it was well over 100, but I didn't make a note of the capacity of this mount. So this is their high-end mount, and I'm pretty sure this one probably has at least 100-pound capacity. It's very large too, very bulky. But if you're looking for a big mount and you want to try the center balance thing, there you go. So again, if you like the well-machined stuff, Los Mandy has had mounts for a long time. They've been out since the 90s, and the mounts themselves haven't really changed that much. They pretty much look the same. So maybe that's why some people tend to reject them, because they do look a little old. But they have the GM8 that's, again, very well machined. And the 8 has a 30-pound capacity. And you can get their Gemini go-to system with this, which has been updated. Then their larger capacity one is the G11. This has a 60-pound capacity. They used to have one called the Titan. I'm not sure if that's still available. I don't have it listed here, so I'm guessing not, but maybe you can find a used one out there. I believe the Titan had an even larger capacity. Then there, of course, there are models from Skywatcher that are very popular. A new one on the scene is the EQAL55i. This one has replaced the EQM35, which I have, which is a smaller, a little more portable German equatorial mount. I actually found it in a yard sale for next to nothing. And this one, like the 35 before it, has a 22-pound capacity. So again, really excellent for small refractors. The HEQ5 goes up to 30 pounds. So again, it can do a bit bigger refractor, possibly a smaller Newtonian, like a 6-inch or an 8-inch. Then they have these interesting ones, the AZEQ5. These hold up to 30 pounds, but they can be configured for alt-azimuth mode as well. So they're kind of like a hybrid mount. They can both do alt-azimuth mounts or German equatorial mounts for astrophotography. Then perhaps the most popular mount from Skywatcher, widely seen amongst amateurs, is the EQ6R Pro. This one has a capacity of 44 pounds, so that's really good for small refractors, larger Newtonians, and even Schmidt-Cassegrains. So that'll do a great job. But if you want even more capacity for larger Newtonians or the really big Schmidt-Cassegrains, like a 14-inch Celestron, you might want to check out mounts like this. I forgot about this one. The AZEQ6, I believe, has the same capacity as the EQ6, but I forgot I put that one in there. And then here's the one I was talking about, the EQ8-R, which has a 110-pound capacity. And then they have a version called the EQ8-RH that has absolute encoders. That really helps limit your need for auto guiding you can do up to 10-minute exposures unguided if you're properly polar aligned, and so you don't really need to auto guide in many cases. Now, of course, German equatorial mounts like this need to be properly polar aligned. And you can do it the old school way with the old drift alignment method, or you can get yourself one of these little handy gadgets. So here's the QHY CCD Pole Master. Of course, they can be easily adapted to their mounts, or well, they don't really have their mount, but they can easily be adapted to pretty much most telescope mounts, as seen here, like on this Ioptron mount. But there are many adapters for a wide variety of telescope mounts. So this little camera has a field of view of 11 by 8 degrees and a resolution of about 30 arc seconds, around, of course, the North Celestial Pole is where you want to point this thing. It has a rough precision of 5 arc minutes. And so, of course, to install it, they're like 3 M3 screws that attach to a mount adapter, again, sold separately. And it's only like 40 by 50 millimeters. And, it doesn't weigh very much either, but since it's bolted to the, screwed onto the mount, it doesn't add too much. And so it comes with a software that, helps you fine tune your polar alignment to really get it down in no time. So you can take the time to, 40 minutes usually to do a good drift alignment, but now you can do this in a fraction of a time with this camera and software. But if you're like, say, Pete Mumbauer or I, or even a few other members in the club, and you just don't want to put up with the lower end mounts anymore from the other companies we talked about, you can go to the high end stuff. So these are the really, really good, well-machined mounts that are just highly accurate and very stable. Like my old Mach 1 has like a 66-pound capacity, and it really is 66 pounds. You don't have to divide that by half. So these mounts have roughly the same capacity for like the Mach 2 here from astrophysics, maybe a little higher, but the 1600 here from astrophysics can go up to 220 pounds. So these are very well machined, very accurate mounts. And the ones from astrophysics specifically are made in the USA. In fact, they're made in Rockford, Illinois. They get some of their components from like Switzerland for like the gearboxes, but largely they're American-made telescopes. They are expensive, but man, they're good. Also very good are the Paramounts from Software Bisque. They're also made in the US and California specifically. They have roughly 3 sizes now. There's 2 of them here. And so this is the old Paramount ME2. There's a bit newer version out today. Looks very, very much like this, though. So then there's also 10 micron. Those are made in Italy. And then there's ASA, made in Austria. So these are European mounts, but not as widely available in the US, but still very, very good. So just a little plug here. Here's the inside of Owl Observatory, our small 12 by 12 roll-off roof observatory at the Kalamazoo Nature Center. And inside of Owl, we have the Leonard James Ashby Telescope, named after our founder and first president. So it's a 16-inch Meade Schmidt Cassegrain with a 4-inch Teleview refractor, specifically the MP101I refractor. The I is for imaging, on an Astrophysics 1600 mount. And on this big mount, it doesn't look like this thing is a 16-inch. So it's a 16 and a 1600 mount. And if you do live in the area, you can take the training course and use this yourself. All right, so let me mention the harmonic mounts here, because I had to add this because these things have become very popular even since the last time I've done the series. I didn't quite stick this in the last time, but I figured I had to do this time. And so we mentioned these a little bit last time in part 4, but harmonic mounts use a strain wave gear system, which combines something called a wave generator, a flexible metal spleen, and a stiff circular spleen, rather than a standard type worm gear. And so, in short, this permits you to have a large capacity telescope with no counterweights. They can be used with counterweights to get even more capacity out of them, but as I mentioned last time, why? If if you have to deal with counterweights, I would still go with a German equatorial mount for the larger telescopes. So for harmonic mounts, they're meant, I think, more for the smaller telescopes, small refractors, smaller Schmidt-Cassegrains, or even Ritchie-Chrétien telescopes or Newtonians and stuff like that. You know, maybe 8 inches and down. Anything larger, I would stick with the German mount. So let's look at some of these here. Ioptron again has many models and many variations of the models. Some include some accessories, some don't, and it gets very confusing looking at their selection of mounts, but they're the ones that have the most available. There's the HEM15 on the top here. So here's the first four shown here. The HEM15 has a capacity of about 18 pounds. The 16C, also 18 pounds, while this one holds 18.7 pounds. So again, very similar mounts. I don't know why they have the differences. I'm sure they have, one has different capabilities over the other, but why build such similar mounts with, you know, and with the same capacity? For me, it made it confusing going through a lot of that because I didn't have a lot of time to do it. And so the 27 here does bump it up a bit. This one holds 29.7 pounds. Again, that's with no counterweights. So that's pretty impressive. Now, there are a few more here. And I didn't really make note of the capacities of these, so I forgot to do that. Sorry about that. And so again, they just hold more and more. So I believe the high end here holds upwards of around 66, pound. It would be nice if it was 69 because hence the number, but it works that way for this one, but it doesn't work quite that way for this one. So I believe this one's around the 66-pound range. So again, they have several models available, and looking at them with all the different options is very confusing. So they should really narrow it down to maybe three, or 3 or 4 models and make it simpler to select one. That's almost why I would disregard one of these, is because you spend too much time looking at them, looking at the options. Now, much more simpler is the ones from Pegasus Astro. There are variations of each of these, but just one of each. So there's really only 2 main models. The NYX88 that holds 31 pounds, and the 101 that holds 44 pounds. Really interesting design too. So these are definitely worth a look at if you're interested in getting a harmonic mount. I have nothing against the Ioptron ones. It's just that there are so many, you don't have time to look at them all. But here, there are really only 2, with maybe a couple slight variations. Then there's the ones that started it all with these small portable harmonic mounts. Of course, as I mentioned in the companion guide, the first ones were from Kronos back in the mid 2000s, and those things were really expensive and really large. You can look them up if you want, but the first of the really small portable harmonic mounts were from Rainbow Astro, and they have the RST 135 that has a 30-pound capacity. It also comes in a variety of colors too. So you can get it in kind of blue or purple or red. So there are different colors available. While their high-end one is the RST 300 that has a 66-pound capacity. So that is capable of holding a pretty large Schmidt-Cassegrain. But if you do put like an 11-inch or even a 14-inch Schmidt-Cassegrain on this thing, I would have a pier, bolted to the ground, not a tripod, because with no counterweights, it makes it very tippable. That's the problem with these harmonic mounts with no counterweights and big optical loads, is they tend to tip a bit. So that's why I think they're limited to the smaller mounts, because why bother with the counterweights with these mounts? I wouldn't. Skywatcher has some very nice ones, and they only have two. The 100i that holds about 22 pounds, pretty respectable for small refractors and smaller catadioptric telescopes like a Ritchie-Chrétien or Schmidt-Cassegrain. And then they have the 150i that holds 33 pounds. Again, very nice design, pretty comparable to the ones from Pegasus Astro. So those are worth looking at. Then I only heard about these when doing a little bit of research for updating the series here. So this is the first I've heard of the ones from Warp Astron. They basically have two as well. They have the 17 that holds 29 pounds and the 20, the WD-20 that holds 48 and a half pounds. So they're very new. I don't know a lot about them, but they are a very interesting looking design. Kind of futuristic looking too. And then finally, the most popular of the harmonic mounts, the ones from ZWO. And they currently now have three versions of these. There's the newer kind of AM3N. That's their smallest version now. That holds about 17 and a half pounds. The original was the AM5, but now they have the AM5N that replaced it. That has a higher capacity at 33 pounds and just released. Perhaps they haven't even really shipped yet. As I talk about this, is the AM7 that holds 66 pounds. So that is a high capacity version. But again, if you put a big optical tube on there, make sure you have a really beefy tripod or more preferably a pier so it doesn't tip over. Because I'd hate to have a 14-inch on one end and no balance on the other end when the thing is tilted toward the meridian. So the whole thing tips over. So there's a quick look at the harmonic mounts currently available. They're all the rage. They are replacing German mounts in the smaller sizes for smaller telescopes. So it is definitely worth checking one out. And they are much more portable too, and you don't have to fiddle with counterweights. So here are some other necessary accessories. You can get yourself some imaging filters. The ones from like Optolong, they're more for color cameras. So they have many versions now, too many to mention here, but the more classic ones are the L Pro. That's more for open clusters, reflection nebulae, and galaxies. So it's more of a light pollution, a general light pollution filter. And then they have the ones more for narrowband type imaging. They have the L Enhance that transmits H alpha, H beta, and O3, all built into one filter. And there's also the L Extreme that passes H alpha and O3. That's better for light polluted skies and more suitable for faster telescopes. And again, there are many more that I don't have time to mention here from Optolong. So you can spend some time checking those out if you get yourself a color camera and you live in a light polluted area. I've heard of people I've heard of one person that does imaging from a high rise in Toronto with a wide field refractor and an Optolong filter, from a very light polluted city. So there you go. Now, of course, as mentioned in part 4, you're going to have to put up with dew, at least, especially if you live in Michigan or another very dewy place. So you don't want to, be out several hours doing imaging and get dewed up, which brings your night to a quick close. So make sure you do have a really good dew prevention system, as we talked about last time. If you do get yourself a good Newtonian, it has to be properly collimated, especially the faster ones like an F2 or F4. So get yourself a good Cheshire eyepiece along with a laser collimator. So, of course, with the Cheshire, that allows you to help line up the primary mirror and the secondary mirror a bit better, while the laser does a great job to help you do that in the daylight as well. So then you can get yourself a focal reducer if you do use a refractor or a Schmidt-Cassegrain. I again highly recommend, if you do select a wide field refractor, make sure it has a dedicated focal reducer. There are generic ones you can get from Teleview that work with other refractors besides their own, but it is really important to have a focal reducer that's dedicated for the optical system of the telescope that you get. And for Newtonian reflectors, you should absolutely get yourself a coma corrector. Teleview has the Paracore. The Batter has their own version. There are others out there, but any good fast Newtonian needs a coma corrector. And if you do wide field imaging, you can use a guide scope. As mentioned last time briefly, many finder scopes can be doubled as a guiding scope, but a lot of people don't like to use guide scopes because there could be flexure between the guide telescope and the imaging telescope, which can affect auto guiding. So be aware of that. But for really wide imaging, I have never personally had an issue because when doing the wide stuff, I pretty much use a guide scope. Never had a problem ever. But for longer focal length telescopes, especially with Schmidt-Cassegrains or similar long focal length telescopes, you're going to want to get yourself an off-axis guider, so you're guiding at the same focal length as your imaging telescope. It's much more precise and there's no flexure. Now, of course, again, as mentioned, many people use an auto guider today. Here's the old Orion Starshoot auto guider, which now is defunct with Orion, but they sold probably thousands of these, so they're widely available on the used market. They do use a small CCD, which is kind of old by today's standards, but they are still very good. And this is the older Lodestar X2, which was an excellent guiding camera, but now, again, many people use the ones from ZWO or QHY for auto guiding. They do have, ones that are meant for more planetary imaging that can be used for auto guiding as well. Now, again, you mainly use an auto guider, but for maybe doing polar alignment without a computer program, or at least aligning your computer for your go-to capability, it's still good to have a good old-fashioned reticle eyepiece handy with the illuminator to illuminate the crosshairs to properly allow you to point your telescope. But back in the day, we would put a star right in the center of the crosshairs and guide it manually with a guide scope or an off-axis guider. But now, of course, we have auto guiders, and no one does their own guiding anymore. It's all done with the auto guider, which is awesome. And of course, there are electric focusers that you can get and programs to help you do the focus for you. But quite often, what's faster is a Baytanov mask. One of these little masks here, like this one or this one, that goes over the front objective of your telescope. And when you have one of these and point it at a bright star, the stars have spikes like this. And as you turn the focus, the center spike appears to move up and down. And you get the center spike here right between the two other crossing spikes. And that's what it's in focus. So I can use one of these a lot faster than a automated focuser with a motor and a program. But it is nice to have when you have to go back and refocus anyway during the course of the night, because that makes the Baytanov mask a bit of a pain because you got to put it back on. And with me, sometimes I forget to take the thing off, and my first image has a bunch of spikes on it because I always forget to take it off. So let's talk real quick about image calibration. I know we're going to run over here. Apologies for that. So you still want to do dark frames. Cameras are getting really good with their noise reduction. With the amount of noise they produce, they get better with each generation, but still, if you take a 5-minute light frame, of your galaxy or nebula, for example, you have to take a 5-minute dark frame. And again, because the noise is random, you want to take lots of them. Usually for dark frames, you want to take up to 20, 30. I've seen people use up to 50 individual dark frames. Now that can get very difficult when you do like, 5, 10 minute exposures and you got to take a series of 5, 10 minute dark frames. That's difficult to do in the field, but if you can continually cool your camera to like -10 or -20, you can have a library of dark frames you can record on like a cloudy or a night with a full moon. So with the cooled cameras, it's good to build yourself a dark frame library. But in Michigan, because we don't get the image as often as we want to, I do what's called dithering quite often. And dithering is where between each exposure, uh, software that is connected to your mount moves the telescope like a little bit in one direction. I mean, maybe a few pixels in one direction and a few pixels in the other direction. And that tends to help subtract the noise as well without doing dark frames. And I've done really good images with dithering as opposed to subtracting dark frames. But it's still good to take a bias images because every camera, no matter how good, has a bias signal. So all digital cameras, again, inherently have a base level of readout noise as it reads the values of each pixel of the sensor. And this is called bias. So it's still good to take a bunch of biased images. But the good news here is the bias images are at the shortest exposure your camera can do. So a fraction of a second. So to take 20 or 50 of these things, it's a very fast process. Not nearly as bad as doing a dark frame. Then there are flat fields. Flat fields help, again, flatten the field. They get rid of the darkened corners called vignetting, or they get rid of dust spots on your sensor. So it's really good to take a flat field to properly calibrate your image to remove any possible vignetting or dust on the optics or the sensor. And flat fields can usually last several seconds, so they introduce noise. So some people do a flat dark frame. I've never found it terribly necessary, but some people do it. But your results may vary. There are many astrophotography control programs out there. For your standard DSLR or DSLM camera, there's old ones like Backyard EOS and Backyard Nikon. I used Backyard EOS for years and really enjoyed it. It worked very well for me. Maxim DL has a newer version out, but it's a pretty expensive piece of software, but absolutely free. Probably the most popular now of the four shown here is NINA, which stands for Nighttime Imaging in Astronomy. It's absolutely free. It's crowdsourced. So a lot of people have put a lot of work into it. So it's a very excellent program that, again, costs nothing. The one I used to use is Sequence Generator Pro. That has an annual subscription fee. And so people have begun to replace Sequence Generator Pro with NINA. But here's a screenshot from our friend Pete Mumbauer in the club here of him one night imaging M67. And so this window here is Sequence Generator Pro. This is PHD2, the auto guiding program. And this is also part of Sequence Generator Pro here, his series of images being taken. And this is the program that controls his dome. But now, of course, today, a lot of people are getting rid of either the desktop computers or especially the laptop computers and all the software and going with one of these Wi-Fi controllers. So the most popular by far is the ZWO ASI Air. I mean, it's the most widely used one by far. This one from Primaluz Lab, this thing costs as much as a laptop. So, I mean, yeah, it makes cable management much easier when you put this thing on top of your telescope. But man, this thing's over $2,200. I mean, I would still use a laptop at the field, save myself some money. But the ASI Air has been very well developed because it's so widely used. So this one can, the ASI Air has a polar alignment aid, a focusing aid, either automatic or manual, auto-guiding calibration, target selection, plate solving, live stacking, auto run. It can help you create an imaging plan, do mosaics, and it can also be used for video or planetary imaging. So this little wonder, it's very small, very inexpensive, just a few $100s, and it has made imaging more popular than ever. You just put this thing on or near your telescope and makes cable management much easier as well. And there's also Cyril. I don't know a lot about that one, but that's free as well. So definitely worth checking out. Here are some image calibration and aligning and stacking programs. Very popular is Deep Sky Stacker, which is free. So that's worth checking out. But here's ones for image processing and also some deep sky stacking. There's GIMP Shop, which is free. You can do stacking and, of course, processing in Photoshop and Lightroom, but most people don't do the stacking with Photoshop. PixInsight can do the stacking. Of course, it's widely used for image processing. This is like the image processing program available today. It does have a bit of a steep learning curve, but once you get used to it, it is a very powerful program, and it's being continuously updated. And it's not even available on a subscription plan. You pay one fee one time, at least for now, and that's it. And you get regular emails about, updates to the program, techniques for processing. So PixInsight, very powerful. And then there's also Star Tools. Now we'll talk about solar system imaging, because many people just love capturing images of the sun, moon, and planets. Of course, the sun, you need a proper filter. So to capture images of the sun and moon, you can do several techniques. You can do afocal imaging. This used to mean you basically hold up your camera lens to your eyepiece, but now today, afocal imaging has kind of resurged in popularity because everyone has a phone built into their camera. So there are phone adapters from like Celestron, Move, Shoot, Move, and Teleview that adapt your smartphone to your telescope's eyepiece and allows you to do lunar and planetary imaging. You can do eyepiece projection, where you connect it to an eyepiece and project the image onto your camera's sensor. So you can do that with a variable projection camera adapter. These work with refractors and Newtonians. For a teleextender, you can use that with the Schmidt-Cassegrain. So the eyepiece goes on in this end here, and then the camera connects here, and then you project the image from the eyepiece and the telescope onto your camera. Same principle here. Then, of course, there are prime focus adapters. Of course, you want to get yourself a good focal reducer for your Schmidt-Cassegrain or your refractor, or, of course, a coma corrector for a Newtonian. But then there are, of course, the T-rings and T-adapters that we mentioned a little bit already. Now, what about lunar photography? Now, of course, today, because your camera is capable of taking thousands of pictures with an average storage card, you can just keep taking pictures until you get the right exposure. But if you want to save yourself some time, you can do a little calculation here. So this is our last equation of the series. So the time in seconds is equal to the f-stop squared. So f is the f-stop. A is the ISO setting, and B is the brightness. So you can put in the number 10 for a thin crescent, 20 for a wide crescent, 40 for a quarter moon, 80 for a gibbous moon, 200 for a full moon. So this will allow you to really narrow down the exposure you need for lunar imaging. Of course, always bracket your images. If the calculation says to use like a 1/25th of a second exposure, do one that's 1/100th and 1/500th, because the conditions vary night by night, and the moon is not always the same exact brightness because it's always a little bigger or a little smaller and so on. So the calculation gets you in the ballpark, but again, do some bracketing. So here's a nice image of the moon that I took. with my old Canon 550D and my old TMB 92 refractor. Just 1/200th of a second at ISO 100. Pretty good. Now, with the planets, today everyone does a planetary imaging with a dedicated camera. What you do is you basically make a video of the planet, like Mars or Jupiter. So you make like a 1 or 2 minute video. And during that time, the video is actually, hundreds or thousands of individual images. And then you use programs like Registax to stack the images. And during the process, it eliminates ones with bad scene. This is called lucky imaging. So today, everyone does lucky imaging of the planets because you can create the video and the software extracts the ones where the scene or the atmospheric stability goes really bad. So the most popular ones are from Player One for starters. I only mentioned the color cameras here, the most recent color cameras. So they do have others. Some are monochrome. Monochrome ones are excellent for solar imaging. So if you do want to do solar imaging, especially in hydrogen alpha, get yourself a monochrome camera. But usually for planetary imaging, most of us prefer to use a color camera and don't want to mess with filters when doing planetary imaging. So there's the Mars C, which is about 12 megapixels. This one is 4.2 megapixels. This is 6.4 megapixels and 9 megapixels. Of course, the more megapixels, the larger the video. So these videos can be gigabytes and just be a minute or two long. They get very large, so it helps to have a pretty powerful computer too. So it depends on exactly what you want to do and maybe your processing capability as well. QHY CCD has several models. Here's a couple of them. The 462, which is 2.1 megapixels. It seems low, but for planetary imaging, that's pretty good. That's really decent. And then this one is 8.4 megapixels. And they each do a certain number of frames per second as well, but I won't bother you with that minutia here. You can check that out yourself. And of course, the most popular ones are again from ZWO. They have kind of overwhelmed the market. There are many more options available here, but again, these are all the color versions. This one is 8.29 megapixels. This one's a whopping 20 megapixels. I mean, holy cow, the images must be huge from a camera like that. And then this one's 8.29. This one's 11.1 megapixels. And again, very popular cameras. There's probably a lot of images out there, but here are some older ones. This is from the old ASI 174, which I do believe is still available. So you can image the Plato region. This is with a 14-inch Celestron and 2x Barlow to give you a bit more magnification to get close-up views of the moon. And again, this is from a video. It's a stack of images from a video using the lucky imaging technique. And of course, you can do the same with the planets. Here's a series of images of Jupiter with an ASI 290 and an old Meade 10-inch or 12-inch Schmidt-Cassegrain with a Celestron Barlow. This is with a 20-inch Dobsonian. I'm always amazed by this one. He must have had a tracking platform, obviously, for his 20-inch Dob with the ASI 224 camera. And here's a great image of Saturn with a 16-inch f14 Newtonian. That must be a really long Newtonian, f14 with a 183 monochrome camera. So MM is monochrome, while MC is color. And I mentioned solar imaging. Here's an old one from using a Luminara camera. Those are pretty much defunct now. I don't believe they're even available for sale anymore. But one of our late members, Roger Williams, he really enjoyed doing solar imaging with that camera. And this is one of his images here that I still share. Out of respect for Roger, he was one of our more generous members with his time and his money. And so finally, keep an imager's log. So your camera records some of this stuff in the EXIF file, but it's still good to keep a log of how you took the image. You can transcribe some of it from your camera later. So of course, the subject, sometimes you might forget what is actually supposed to be in the image, especially if it's a faint target. So it's good to record that for future posterity in case you don't get to process it right away. Write down what you're actually trying to take a picture of. Make a note of the date and time. Of course, the camera will do that if it's set properly. Make a note of your location, the current sky conditions, the transparency and the scene, what camera you use, the exact instruments, the telescope, focal reducer, chroma corrector, etc. The length of the exposure. Again, your camera will do that for you today. The filters, if any other accessories like a Barlow lens, and maybe just a few basic notes of the type of processing you do. So ultimately, we all strive to get to images like this. Here's M13, the Hercules cluster. This is a 9-hour exposure. This is NGC 6744 in Pavo. Not really accessible from Michigan, but this is a 17.5-hour image from Don Goldman from Astrodon. Here's another one from Don Goldman of the Orion Nebula. And all those images were taken with a system very much like this one. So this is the KAS remote telescope, which is a 20-inch plane wave corrected dull Kirkham and a Takahashi. We currently use SBIG STX 16803 CCD cameras, but we are in the process of replacing those with more modern, lower noise, higher sensitivity CMOS cameras. And we have this on a Paramount ME2. So again, if you're a member that lives in Southwest Michigan, you can use this telescope. And again, we're going to do some big updates here in the months ahead as I record this right now. And this telescope is at Arizona Sky Village, which has very dark skies. So here's an all sky image taken from Arizona Sky Village by the late great Terrence Dickinson using the 8mm fisheye lens. So that's just some of the high-end imaging that many of us strive to get to. But I think many of us will be very happy with either a camera on a tripod or a small refractor on perhaps a very portable harmonic mount. So thank you for joining me for all 5 parts of the Introduction to Amateur Astronomy lecture series. I hope you learned something, and I hope you keep learning. And if you ever have any questions, please feel free to contact me anytime, and I will do the best I can to answer them. So keep looking up.